very much. And a simple example we'll come back to is here is the Quasar lens 2237. This was somewhat of a surprise in the CFA redshift survey. They went and took a redshift of a 15th magnitude spiral galaxy at redshift 0.03 and discovered it actually had a redshift of 1.7. Because buried in the middle of this galaxy on scales of only an arc second or so right in the core were 4 images of a quasar. And so this is what it looks like in the optical, although superposed here is a contour plot on the other side. But so here's the DC image, and if you look at it with HST, it's easy to see there's a lens at the center, although you still have a fair amount of work. But if instead I just look at the part of the flux in this image which is time variable, that's what I see. Okay? And right, we're done. Right? There's something time variable here which is a complex of point sources. And that's what a quasar lens is. Okay? And that's the basic scheme, and so now we'll spend the rest of the time boring you with some details. The challenge is that if you go to 23rd magnitude, which is about the level where something like LSST can sort of monitor the sky with, say, 10% accuracy without any particular difficulty, you have about 100 quasars per square degree. So about 1 in 500 of those are lensed, and so there's about 1 lensed quasar for every 5 square degrees on the sky at this level, and so there are about 10,000 lensed quasars on the sky. The problem with lensed quasars has never been that there's any particular shortage of them. Even though they're relatively rare compared to galaxies, it's just that they're relatively hard to find if you go fairly faint. Because right after 25 years of effort, there are about 100 lensed quasars of all varieties. And the largest systematic surveys right now is the Sloan, is still somewhat around 30 lenses. And I should say, is everything I'm going to say here applies equally to Greg's problem, is this would trivially identify lens supernova as well. Although it doesn't address this question of trying to flag it and get like a time delay out of it at the top. Okay. I'm not going to spend too much on uses. Various people have mentioned it. At least for the quasar lenses, you would tend to automatically get a time delay from the data stream, just because you have 10 years of monitoring data of the thing at the end. And you still have degeneracies between the scale of the universe and H0. And the surface density of the lens, but you can imagine using some of the self-calibration schemes from, say, searching for clusters or calibrating clusters to get rid of some of those issues. You can look for the structure of the lens, and sort of what we're actually more interested in the quasar lenses at the moment is that there's all the, aside from cosmology, there's all this rest of this stuff in astronomy. So one of the things we're most interested in right now is we use these things to study the structure of quasar accretion disks using microlensing by the stars in the galaxy. And so here, for example, is what we can do now. So here is the size of an accretion disk at a rest wavelength of about 2,000 angstroms versus the mass of the black hole measured with microlensing. And we can do this for about 10 systems right now. Starting to do it as a function of wavelength, but there's no reason with sort of 10 years of LSST data you can't do this for several thousands of objects over a much broader range of black hole masses and accretion rates and things. And so it's sort of an application which is somewhat non-standard. Okay, so why is it hard? Well, if you just go out looking for lensed quasars, the first problem is you have all sorts of unpleasant backgrounds. So there are considerably more, for example, quasar-star pairs than there are quasar pairs or lenses. Survey image quality at the moment is really not quite good enough to go looking for lensed quasars. Sloan's typical seeing is not quite good enough. You'd really like something that is at least marginally sub-arc second rather than significantly over arc second on average. Particularly as you go to fainter and fainter quasars, you have the problem that the galaxy doing the lensing will increasingly start to mask the presence of the lens. So for example, if you're doing color-selected quasar lenses, by the time you start going beyond 19th magnitude quasars, the lens galaxy starts pushing the quasar out of the quasar color space, and so you'll stop selecting it. Similarly, if you have absorption in the lens galaxy, that will also change the galaxy. And then it suffers from the same thing of all of these things. You can call it the Swift curse, that life is easy when you have 10 objects, but as soon as someone hands you 100 gamma ray bursts in a year, you can no longer do any follow-up. And this, of course, applies to any of these projects, which are going to go from tens of objects to hundreds or thousands of objects. Okay, now if we consider the future surveys, which everyone's been mentioning, most of them have some sort of a time domain component. And the sort of degree in which they're doing it depends on the exact survey. So for SDSS, it's the 200 square degrees, roughly, of the equatorial strip that was used for the supernova survey. So it's good coverage, relatively good cadence for this project, still not quite as deep as you'd like to go, and the bad resolution for this particular project. DES will have some sort of time component. Okay, that's not exactly nailed down, but some, say, 50 square degrees that we regularly survey for supernova. And of course, LST and pan-stars have sort of roughly all sky, or most of the visible sky coverage. And so what you want to do is, instead of looking for the lenses in the DC image, the coad image, you want to look for the lenses in taking the coadded image and subtracting it from all of the epochs, because that pretty much eliminates almost all of the sources on the sky. Okay? And then the things which are the lenses are the things which are not point sources. Okay? So you simply look at the time variable flux and just look for the things which are not point sources, and by and large, those will be the lens galaxies. What sort of variables do you have? Well, you can have, instead of worrying about quasar star pairs, you have quasar variable star pairs, but variable stars are like 1% of stars, so you've suppressed that background by a factor of 100. You have variable star pairs, right? Those are down by a factor of 10 to the 4 compared to star pairs, even before you worry about any sort of color selection. You can start worrying about quasar supernova pairs. That's probably one of the more significant backgrounds. So you have like a Seyfert galaxy, which is where the center is varying, and then you have a supernova go off in the galaxy, and that will show up as an extended variable. There are binary quasars, which are a significant source of contamination on 3 arcsecond scales and above. And then, of course, you have the lens supernova. Yeah?
But they go away. Like the supernova eventually goes away. So
Yeah, so from the light curves, you can probably figure it out. So, and the colors, and there's lots of information once you know you go and look at them. Imagine it's actually mostly semi-automated. You can write a pipeline to clean most of this up pretty easily. And this just sort of illustrates what you're fighting against. So here versus galactic latitude, here are the number of stars per square degree going from 19th to 24th magnitude. Right? Variable stars are down around here. Variable star pairs are way down here in terms of number. Here is sort of the surface density of quasars and crudely the surface density of lensed quasars. And so if you're working at 23rd or 24th magnitude, the surface density of lensed quasars is well above most of the backgrounds, and so you just don't have much left to worry about. Here are some illustrations. This all uses the source of all perfection is involved. So this comes from Alard and Lupton originally, and, which is just difference imaging, that basically you can rescale an image in its PSF structure and its flux to more or less perfectly subtract things. And if you want a good example of how well it subtracts things, this is a field in the galactic bulge that is being monitored for galactic microlensing. And so basically an infinite number of stars per square degree. Okay? And this is not even really stretched to show all the stars, right? This is just completely filled with individual sources. Right? That's what's left after you take and only look at the AC image. This is actually the microlens, and then there were 3 long period variable stars in the field as well. And then if you go and analyze the structure of those images, they're all basically point sources, and so therefore not lenses. But you can see the huge reduction in any sort of flux on the sky you get by this relatively simple trick. And we've done this for the lenses we've been monitoring for other reasons. These are now all high galactic latitude fields, so there's not as much garbage in them to begin with. But here's one, so that's the DC image. In the AC image, all you see is the complex of quasar images. Here's another one, okay, sources. In the DC image, AC image, all you see is the quasars. Okay, here's 2237 again, so you can even make this huge lens galaxy vanish, and all you see is the quasar hiding in the center. So we've tried testing this, or this is as far as we've gotten in implementing this, is we took, at the time it was the public data for the SDSS supernova survey, so it was a limited number of epochs. And what we did is we took the lens candidates from the SDSS quasar lens survey in that field. It turns out there were no confirmed lenses in the monitored strip. Okay, so we took the candidates, all of which had been rejected on other grounds as not being lenses as part of the survey, and said, well, let's just go and see if we can reject them using this technique as well. And so there were 36 candidate lenses in the strip, and basically we just did is extracted a field around each of them and applied this technique to it. And here's roughly the way we did it. So first you take everything in the fields and identify those which seem to be time variable. Then we said that for current purposes, we don't really have that long a stretch of data, And really all we want to do is we don't really want to pay any attention to periodic stars. And so we can get rid of most of the periodic stellar sources by just looking for things that have sort of smoothly varying long-term trends rather than short period things. So we just looked for things that were better fit by quadratic polynomials than a straight line as our sort of definition of things that were possibly quasar candidates. That could be done much more elegantly. And then we then constructed an image of the time variable flux and then just looked at the forward path max, the half-light radius, and the ellipticity of the variable flux as a way of identifying the objects. The main limitation here is we're really only dealing with between 10 and 20 epochs of data for these. And so if you go to the limit of where you have 200 epochs, all of these results will be much cleaner. Okay? So here's the variability in these fields. So here's the Sloan magnitude of these objects. Here's the RMS variability. So we chopped out these objects as variable, and they're color-coded in ways you probably cannot decipher. But the blue circles are the SQLS lens candidates. We also tracked all of the other SDSS spectrographically confirmed quasars in the fields for the red dots. And then the green crosses, which you probably really can't see, are the ones that are eventually flagged as looking like they're not quite point sources. Okay, so we chop out those. Then you look at for the things that are better fit by a long-term trend. Okay, so this is just sort of an F-test for whether you're better fit as a straight line versus a simple polynomial. You chop out the things that sit down here. Right. And then you look at the flux structure in terms of the half-light radius and the ellipticity, and you sort of chop out that region there and ask who's left that made it through all three of these cuts. Okay. And just to give you a sense of where he stood, if you take all of the fields, which are about 3/4 of a square degree, in the end we had light curves for 15,000 objects in the field, and the number of objects that made it through all three cuts was 1. Okay. If we did it for the lens candidates, because we're dealing with not only 15 or 10 or 20 epochs, not all of them show up as the variability, so we don't flag a number of them as a variable. But of the 14 which are variable, right, none survive. If we look at all the SDSS quasars, in fact, one of those is one of the ones that survives as being variable and slightly extended. It's not compelling. It just looks like it's not really a lens candidate. You don't look at it by eye. And so it's really quite efficient. It's basically 3/4 of a square degree. Basically, we had one false positive. And so that would mean if we did this to the whole 200 square degrees of the Sloan region, you'd be talking, a couple hundred false positives, even using only this very limited stretch of data. If we now went back and redid it with the full 30 or 40 epochs from the SDSS survey, that should clean up the false positive rate considerably. Just to give you a sense, here's what some of these light curves look like. So here's the light curve of one of the lens candidates. So these were the early equatorial strip observations. Here are some of the initial supernova observations, and you can see basically you saw this nice brightening over the years between them. So that flagged as a good quasar candidate. Okay, and then you go and look at it and you find that it's a point source. This is the one that was the spectroscopic quasar and showed some variability, but was then a false positive. And then here's one which just really wasn't doing very much significant and wasn't flagged as variable, for example. All right, so summary is despite using only a subset of the data, this works pretty easily. Right? By the time you decide on what the cuts are, it's really pretty all automatic. You just get to the end and it spits back this handful of candidates to go and take a second look at it. And we confirmed that at least for the ones which we could flag as variable, that the SQLS candidates are not eliminated. In fact, the supernova survey people did serendipitously turn up a real lens, okay, which was not found by the SDSS people. And that one does show up as an extended variable source when we go through this analysis. So there now is a lens in that field, and we would have found it had we applied it to the whole strip. And we're working, the main problem is finding someone who has the time to do this, to try to run it on the full region. It's a kind of limited interest to do it for the full region, unless it stays fully automated, because you're really only expecting to find a couple of lenses in the whole area, given the depth limitations of Sloan. And as seen from the previous talks, other than as a proof of method, it's not that interesting to find 1 or 2 new lenses at this point. And that was it.
You know what your false positive is then when you look at this person?
Just look at crap. obvious. It's just
So how can you change your flux to turn it into a real?
what you really want is you just want a longer light curve. I mean, the reason we didn't obsess about it is that's clear. Most of the problems come from doing this with 10 or 20 epochs. And so the right answer is just to do it with a better data set than to obsess about why this one snuck through. I mean, typical quasar, I mean, if you did this on LSST timescale, so a typical quasar varies by 10% per year. They don't all do that. So over 10 years, basically, we'll flag essentially every last quasar as variable.
So given what we know about quasar variability,
Yeah, so over 10 years, you'll flag almost all of it as variable. And in fact, the quasars, right, are more variable. The lensed quasars are more variable than unlensed quasars, because even if they're not intrinsically variable, microlensing will also make them vary at that level over 10 years. And so then it's just a question of, can you resolve them? And so, if you take LSST with, say, a arc second PSF or slightly less, all you have to do is recognize that it's not a point source. Right? So you don't necessarily even have to resolve it. So your completeness for anything bigger than about a half an arc second should be very high. And then you lose them as they become so small that you can't recognize that it's not a point source. But we know from class or whatever that the number of lenses as you go to small separations is just dropping as a power law as you expect. So there aren't a lot of lenses down there too fine.
I did want to ask about the time baseline. It looked like you used like the last year's only one and then this first year of the
we just use the first public year of the supernova.
So did they just not release any of the previous years for that
We
reason?
just made an executive decision to use the public data.
I see.
We may switch that at this point, but
Because I mean, you could, depending on the area of the strike, you could go back. You could have four or so years
Yeah.
for any given points.
no. It's just a question of how much rework we want to do after getting the referees input.
We have up to 140. We have a lot more epochs.
Yeah, no, and that's clearly the solution to the issues raised.
Yeah, this might be a question, but did you pick out galaxy lenses that are variable because of
Galaxy lenses that are variable because of
microlensing?
microlensing of what?
So if you have multiple image source, it's popping out, right? Or is there a solution?
I mean, like Tommaso and company's lenses. I mean, I have to have something to microlens, which is bright enough to see.
So you have a galaxy behind a galaxy, which doesn't, the galaxies don't vary, so your method will go.
That's right. So it won't find those. You'd have to have in the galaxy. You would either have to have an AGN in it, or would have to have a supernova in it. So if it had a supernova, you'd find it
No,
without
I'm
any trouble.
thinking about the stars in the galaxy.
Ah,
the
the
surface right
galaxies
space
themselves.
missions are
The Great Merle Escudé paper. In theory, I don't think it works for clusters, I don't think it works for galaxies, but in theory, if you have something lensed by a cluster, the scale length of the magnification for a cluster caustic can be so big that you can magnify a red giant at redshift 2 to be almost visible.
Drifts across.
So to be almost naked eye visible,
We
but the
see
event rate
flux-
is really low.
We see flux changes in individual images,
No, it's going to be too.
microlensing, so.
No, it's going to be too small, re-adding incoherently. But the one thing is there is this theoretical scheme that at least for a cluster caustic, it is possible, if you don't get too bogged down, to take a red giant and magnify it enough to produce a visible effect. And then the question is, which I think was going to be Jordy's paper 2 on this, but I don't think he ever did, was what happens when you allow for the fact that there are other things in the cluster that make the caustic have some structure that would wash out some of this effect.
So if you compare a survey like DES, which is going to do a limited number of repeat observations with something like LSST with the many exposures, what's the, if you could choose between 10 and 100, then what's the plot of number of things you discover as a function of number of exposures?
We would try that. It becomes simpler and simpler as the resolution goes up. So But what sort of kills you here is a small number of epochs, plus Sloan does not have the right resolution to look for lenses. Right. And so if all the images were consistently sub-arc second, right, then if you go to, lost it. Right, so the problem is in this space, right, what's a Sloan pixel, Bob?
0.397.
Yeah, okay, so this is 0.4 arc seconds, 0.8 arc seconds, these are 2 pixels already. So this is already 1.2 pixels, and so median seeing is sort of, this is the half-light radius of the typical seeing, right? And so that's right around down where you're looking for the lenses. And so if you could sort of take this cloud and shrink it down into this box by a factor of 2, which is roughly the sort of improvement in resolution you're talking about, then you could get away with many fewer epochs.
So we're thinking of this about the band spec, right? And so even if your PSF is pretty big, the pixels are small enough that your PSF is getting better sample effects. So
Yeah, so
you can find smaller deviations from point source.
right, but so then you need more epochs, because basically it's a question, you need to build up the signal to noise of the AC image to the point you can recognize a deviation from the whatever the time average point spread function.
But then, of course, you have to know you have to know your PSF across the image pretty well. But over those nice
Yeah, well, it all depends how hard you want to push down under the PSF scale. I mean, look, if you're looking for things that are half the size of the PSF, that's really never very hard for sort of equal brightness objects. So.